e to the zeta, if you look at its real component functions, right? Those real component functions are solving a system of PDEs. What are they? Well, one thing they're solving is the Cauchy-Riemann equations over H3.
Yep.
If they solve the Cauchy-Riemann equations over H3, they're also going to solve the A Laplace equations for H3, as we discussed, right? There's, I don't know how many of those. We found them the other day.
Yeah.
I think 3.
Yeah.
I think 3. But the point is, you could look at the differential consequence of the CR equations, and you could say, well, it solves all the differential consequences of the HCR equations, you know, because once you solve one differential equation, you can take that differential equation and differentiate that thing, and that's another differential equation your solution solves.
Yeah.
There's kind of no end to this. But more interestingly in 51 is the d eta, d zeta equal to eta term. Those are also solved, right? And those are the ones that we can't obtain as just like CR equation or a Cauchy or a Laplace equation, because those are not homogeneous, right? In terms of like ux equal to u, vx equal to v. See, these are differential equations in the sort of genuine sense that they're mixing terms of different homogeneity. I mean, I don't know, just a thought. There's your Larry, Moe, and Curly functions.
Oh yeah.
52. And those multiplied by arbitrary a plus bj plus cj squared gives you the, you know, there's this. So here's what it works out to: e to the zeta. Here's the component. This is what the component functions to e to the zeta look like here: e to the x g1, e to the x g2, e to the x g3. All right, and I actually think G1, G2, and G3. Well, anyway, let me not say more. Yeah, I have nothing to say. But there it is. I mean, there's the explicit solution. That's the general solution to this differential equation right there at 54 in all of its glory. I mean, so I mean, take these for what they're worth. I'm just trying to showcase, like, don't mistake what we're doing for just being calculus 2 all over again. I mean, it is that at one level.
Yeah.
But if you dig down into like the component level, there's a lot going on. And I mean, there is certainly like incredible similarity and like regularity to what's going on too. I don't think that all PDEs can be lumped into this kind of structure. But a giant open question still is like, what is the right machinery to attack this problem to say, aha, this system of PDEs does have this structure? I don't know the answer to that question yet. I'm still working on that. But anyway, here's theorem 4.3. Theorem 4.3, if you look at it, I have d eta, d zeta is f of zeta, g of eta. So what is that? You're like, couldn't you use letters that sounded different? d eta, d zeta equals to f of zeta, g of eta. So, in other words, the derivative is equal to a product of functions of each of the variables. So in this kind of scenario, you can separate and integrate, right? That's still, it is legit over the algebra for the same reasons as legit over the reals, which ultimately rest on the chain rule. It's pretty much because the chain rule is why that works. But I would also point out that the devil's in the details. In the usual case, you separate variables, right? So I don't know if you thought about this or not, but this one, for example, dy dx equals to y. dy over y, right? dx, integrate. So we get natural log, absolute value of y.
Equals x plus c.
X plus c, right, great. So we exponentiate both sides, right? We get absolute value y equals e to the c times e to the x. So y is plus or minus e to the c times e to the x. So we'll just say y is equal to like c1 e to the x, right? There you go.
Yeah.
However, c1 is plus or minus e to the x.
Yes.
E to the c rather. That is non-zero. So technically, this derivation does not allow y equal to 0 as a solution. But is y equal to the 0 solution? We'll look back at the original problem. I have the function identically equal to 0. Is the derivative of the 0 function 0?
Yeah.
Sure. Is 0 equal to 0? Well, I'd like to live in a world where that's true. So yes, the 0 function solves this differential equation.
Oh, if x and c are inverses. So if you want crap.
See, the reason that this happened to us, the reason that we didn't get 0 in this line of logic, if we carefully study it, it's right here. Going from here to here, see, we divided by y. And so once you divide by y, you've lost information about y equal to 0.
Oh, because you can't divide by 0.
Right. And that's why, it just so happens, we're fortunate, the quirk of fate, that if we're just kind of like, oh, I'll just call it C1, and then we just let C1 be 0. It's just a quirk of the relabeling that brings 0 back into the story. So this one here, strong suspicion that there could be exceptional solutions where g of eta was like, if g of eta is like a 0 divisor for certain choices of eta, that probably needs to be treated as an exceptional case. So if I was to study these more deeply, I think that would be something I had to spend a lot of time like looking out for. In the regular differential equations, you just have to think about, well, we're going to lose a place where this is 0. Not so bad, right? 4.4, there's your integrating factor.
Yep, that's what I noticed.
And it works for the same reasons it worked before, because that calculus that you did still holds here.
You know we're in algebra? There's some, well, I guess like a certain line of work I can see, but there's some things that don't cross over in calculus. Especially like, yeah, what if it's only like right differential?
Well, the thing is, I'm working on a commutative algebra.
Okay, yeah.
But yeah, very good. The exponential, you have exponential of integrals, so that the whole just song and dance I told you about the 0 divisor in the previous one, that actually is absent from the integrating factor argument because we multiply by the exponential of the integral of p d zeta.
Yeah.
It's an exponential. That's in the units, so like we're not losing information when we multiply the differential equation by that. So actually the method of integrating factor is more robust in terms of like keeping track of the solution set during the procedure of the method as opposed to separation variables, which can lose extraneous stuff. Also, of course, separation variables is just really nice and like super easy, but oh, look at this. Now theorem 4.5 is the exact equation. All right.
Oh, yeah.
Yeah. So m is partial f partial zeta, and n is partial f partial eta. That is a kind of fancy way of saying, I mean, you could check that if the mixed partials were equal, right?
Yeah.
If partial m partial eta was equal to partial m partial zeta, that, I haven't worked this out, but I believe that would be a sufficient condition given certain topological presuppositions that there exists this big F that, but that's stuff I haven't really fleshed out. Okay, that's, I've been careful to say that
Should give an example of it.
If there exists a function f such that the partial derivative gives you the m and the other partial derivative gives you the n, then f equal to a constant is a solution to m d zeta plus m d eta. So actually, I just haven't bothered to get into the tests for exactness in this paper. All right, you could look at that if you wanted. I don't know if I ever really have that deeply. My intuition is that there's nothing there that's not already there. But I shouldn't think that. I should think how do zero divisors mess this up is what I should think. How can I make zero divisors mess this up?
Well, if the partial gives you a zero divisor, it should mess it up.
So here we go. I think we just found our first genuine project. Theorem 4.5. Can we get test for exactness and ruin it with zero divisors? Okay, so a more responsible statement of this goal would be study the test for exactness in the presence of zero divisors. And how does it change, right? How do we prove the existence of f in the usual scenario, right? Does that proof survive to here? This actually could be something, Audric. Now that you mention it.
No, what I was thinking is that if you have a partial, because it's the partial of dn or partial n has to equal to partial. I gotta look it up.
I know what you're saying. The mixed partials.
But if one of them gives you a zero divisor, the other one doesn't, it should mess it up, I think. Because then. So partial m of partial y needs to equal to partial n of partial x. So
here's how, if you really want to crack this problem, here's what you have to do. You have to go back to differential equations. And you have to understand, you have to ask yourself the question, how do we know the standard result? What logic does that rest on? Right? And then the question becomes, can I adapt that proof over the algebra? And you might find out that it's already something that fits into the framework that I've shared with you. You might find out that there's a concept missing that we need to define and develop. I don't know right offhand. I'll have to think about it. So I think this is great, actually. We'll see what comes of it. What's this 4.6? Oh, this is an example of an exact one.
Yeah.
Ooh. Oh, 2 eta d eta plus 2 zeta d zeta in hyperbolic numbers, huh?
So for that question, we're trying to get something that should give us an exact, but isn't solvable.
We would like to understand if there is an exactness test and if it needs to be modified because of zero divisors. Like you said, usually it's that partial m partial y equals to partial n partial x. Is that enough? But here I think it would be partial m partial eta equals to partial n partial zeta.
Yeah. Yeah, but you know, partial f partial yeah. Was it partial f partial zeta needs to be equal m of x or m of eta zeta, and partial f partial neta needs to equal n of zeta. Right, I think so. Yeah. Yeah, you said that here. So should if you have that condition,
Or alternatively, what condition do we need for there to exist such an f? That's like the more general kind of version of my questions. I say, if there exists this function such that blah and blah, then, you know. But,
so if we have m and n and they have the exactness test, how does that, we're trying to prove that that always gives us an f? Or we're trying to see if it always gives us an f?
well, the way I have the condition stated here, I say m is partial f partial zeta, and n is partial f partial eta. So when you look at m d zeta plus n d eta, that becomes partial f partial zeta plus partial f partial
Partial f partial zeta d zeta.
Oh, so that is quite the this.
Yeah.
So this is quote unquote the total differential of f.
Yes.
But you know, this this is, I don't think, to be honest, I don't know if I've really totally thought out this stuff, because this is f is a function from a cross a to a, I guess, and so I think that this is true. If like this has variable zeta and this has variable eta, I do think it's true that the total differential of f would naturally be this thing, where the total differential again is the differential from advanced calculus or whatever, and to be more I could descend down further and look at this in terms of its underlying real content. See, this is Rn cross Rn, right? And so like this really is got like f1, which is a function of x1 through xn, y1 through yn. The level of real component stuff. There's a lot of moving parts. So when I talk about df in terms of the real calculus, the natural thing would be something like, okay, so this is partial f partial x1 dx1, partial f partial x2 dx2, and so forth, partial f partial xn dxn, plus partial f partial y1 dy1, partial f partial yn dyn. But if f is adifferentiable, then because of the a-Cauchy-Riemann equations, these can be like basically partial f partial zeta is partial f partial x1, and the rest of these, if we're assuming one is the identity, right?
Mm-hmm.
Then this can be kind of rewritten as like partial f partial zeta times like dx1 plus v2 dx2 plus vn dxn, right?
Mm-hmm.
And then that is what we call d zeta, and then the same thing can be done for that. So that's why df is partial f partial zeta d zeta plus partial f partial eta d eta. You just got to understand that this d eta is actually this monstrosity of dy. It's an algebra valued differential. So that'll be that. You know, okay, so that's df. And so if, how can I say this? All right, so the point is if m dx, if m d zeta plus n d eta is equal to this by assumption, and then by the calculus here, that's equal to df. That's why if f is just equal to a constant, well then this is clearly 0, which means the original differential equation has a solution as a level set of f of zeta, comma eta equal to a constant. I have not answered the question, what does it take for there to exist an f such that m is equal to?
Yeah, this will be something else. I have like a whole bunch of calculations on that wave equation stuff you've been doing. I was trying to not find. I would not the polar coordinates, but I'm not gonna lie. I tried to plug Heisenberg's uncertainty principle into it. And I was just like, because something about it just made me seem like since you can have two answers, like when it pops out, or like when you solve for it, like it give you a one term and a two term. I was like, what if you can solve one for x and one for time? And I was like, then you could have a wave and solve it for position and time by using isomorphism.
It's strange to think of time as a function of position.
But if
You know?
yeah,
But the mathematics
it should
doesn't
work.
distinguish, does it?
No. Also, I was breaking my stepsister's head with that stuff because I told her that time is the way we see it is like just a human construct, but the only way to prove time is change. If something changes, that time's then that's our definition of time. Is just change.
Yeah. Yeah, I don't know. I know there's something beyond time, for sure. And
no, I was just saying.
Understanding that,
yeah.
Goodness.
No, but yeah. So I tried doing that, but I was looking at differential equations, and one got me pretty far, and then I got stuck somewhere. Because I got stuck somewhere trying to rewrite it there like that, because I remember I wrote down what you said when you were trying to solve the original one, and we were trying to look for characteristic equations, but we kind of got stuck. I just looked up a whole bunch of hard equations on the Wikipedia page, and I just went through the lines with that equation, and it got pretty far, but I couldn't pull something out. So.
Yeah.
I doubt it'll pull out anything, in all honesty, because
the usual proof
uh-huh.
For the exactness condition working, it has to do with Green's theorem.
Okay.
If you look it up, it ties into this discussion of conservative vector fields and path independence and all that. It's part of that story. I don't know to think more about what I can say about the algebra plane. What can we say about a squared? A cross A. I don't have a good answer for you on that. I just know that if I ask this question, what's the exactness condition, then I need to study the calculus on A cross A. I'm being led to that.
It's R cross R. What's R cross R?
Depends.
Right? It's just a plane and do things on it.
But in R cross R we have we have a curve, we've got an area, we bound the area by a curve, and so we have all these lovely theorems that relate the integral around the edge to the double integral in the interior, and those things through Green's theorem tie into this story about the exactness of differential equation. In any event, so this example 4.6, all I'm doing there is I'm saying, okay, we got 2 eta d eta plus 2 zeta d zeta, right? That's a differential equation in H. And I'm like, well, the solution, I can make my f of zeta eta, eta squared plus zeta squared.
I don't know which equation I plugged in now, because I don't think it was Heisenberg's. I'm not sure. Schrodinger's just the wave one, right? I plugged some random physics thing, or it looked like a wave equation, and it looked like the wave equation.
Yeah, the Schrodinger's equation is like time derivative in time derivative.
Because now I was thinking about Heisenberg's. I was like, no, that's not an equation. That's more like a principle.
I want to say Schrodinger is first order in time.
Second
order in other things.
I was watching a video and I was like, hey, that looks like something Dr. Cooks did. And it matched up with something you tried. And I was like, so I just tried it again and I couldn't get anything back. I can't remember what it was because it was late at night. I was just watching YouTube to go to sleep, and it piqued my interest.
I hear you.
But yeah, because I was thinking, I hate physics sometimes. It was what was I doing? I was I understand that
Mm-hmm.
given the limitations of experimental physics that you shouldn't be able because how the wave works how I explain it, how I think about it, it's if you hear a sound, you for a short amount of time you know where it came from, but you don't know what pitch it was. But if you want to hear the pitch of it, you're gonna know it's got to ring out. It's got to ring out more, but you're not gonna know where the pitch came from if it rings out for longer.
Right.
And so I was while that makes sense in the limitations of our world, I feel mathematically you have to be able to pinpoint a position. There should be both. There should be something mathematically that hits both. While it might not be physically, because when they redid
well, I just the way the mathematics works is the the observables have to be their eigenvalues of the operators which we observe, and to know eigenvalues, the only way you can know eigenvalues of two different linear operators at the same time is if you can pick a basis in which they're simultaneously diagonalizable.
Yeah.
And
why wouldn't you try geometrically then? Why wouldn't you try to?
But anyway, it turns out that you can only pick a simultaneous eigenbasis for two linear operators if they commute. So that's why you can't simultaneously measure. You can't have a quantum state which is both a position state and a momentum state at the same time.
Yeah.
Because position and momentum don't commute. The one is something it depends on what basis you pick, but
no, but that
one is kind of a derivative with respect to x. The other one's.
But we're not trying to push it into a different algebra though.
I'm just saying if you use regular quantum mechanics, you're
Yeah.
stuck. I mean, it's just,
Yeah,
it's
like
just the mathematics of it.
Yeah, I don't know I'd have to.
Now, if your intuition is that like quantum mechanics is wrong, then like we should be able to measure both. Well, that's just a very classical thought, and I mean I approve.
Yeah, but I have to do more. I don't know. Maybe I'll do that like as a research if I get far enough into math. No, because it doesn't make sense. Because what was it that I remember my teacher in AP Physics. He was like, technically you should be able to go back in time because like you can just rewrite everything as a like if you look at a position graph, and just keep a line going. Like if you he said if you threw a rock off a cliff, you could retrace a parabola. That's what he was saying, like, you should be able to do that. But he says, like, you get he was talking about how you get, like, negative mass or something. He was like,
yeah.
He said, like, you get stuff that just doesn't exist.
Seems like I'm writing them in, this is like the x and the y, then the x term, but
Yeah.
So this is my differential equation.
Mm-hmm.
So here's my m, here's my n, and the claim is f of eta equal to zeta squared plus eta squared does nicely because partial f partial zeta is 2 zeta, partial f partial eta is 2 eta, so as you can see, bam, right? And so really, this is the differential of zeta squared plus eta squared.
Yeah.
And what's the solution to this? Well, it's just zeta squared plus eta squared equal to a constant. And actually, I said this example is over the hyperbolic numbers. Does it have to be? Like if you really think about it, this calculation is fine for any algebra. Actually, this is a differential equation you can define over any algebra. And what this solution set looks like in different algebras is quite different.
Yeah.
Because these are squared algebra variables, right? So like it looks pretty different in the hyperbolic versus the complex versus the null numbers. The equations I have in that example are for the hyperbolic numbers. And like I show, it ends up being u squared plus x squared plus y squared plus u squared plus v squared equal to a. And 2xy plus 2uv equal to b. So here, the a and the b are this c is a plus jb. That's what's going on there. And then this solves. So this you could rewrite as like d zeta. Do I do d zeta d eta? Oh, d eta d zeta. So if you solve that for d eta, you got d eta d zeta equal to what? Minus zeta over eta, right? That's the differential version of this. I might call this the so-called Pfaffian form of the differential equation. Pfaffian. Pfaff was an early mover shaker in the world of differential forms and such. So the point is, anyway, that like if you break out what d eta d zeta looks like, d eta zeta equals to minus zeta over eta into components, we get ux is yv minus xu over u squared minus v squared, and xv minus yu over u squared minus v squared equal to vx. I mean, so like they're coupled, nonlinear first order differential equations, and yet the solution, here it is, pace out. And that brings us to section 5, which I am most proud of section 5. Maybe section 5, let's see here. Section 5.3 is what I think is actually most, I think it's the coolest thing that we've done. It's just so cool.
5.3.
Yeah. Hmm. See if I can. Let me see if I can explain it to you without doing everything here right now. Okay. We can. Then we'll go back to the start of section 5 and like do it carefully next time we meet. So, does that sound good or no?
Yeah, that sounds good. So if you have a differential operator acting on an exponential alpha zeta of f, and f is a what? A function?
Where are you?
I'm on 5.3, the proof. Well, I'm looking at the proof, but I'm trying to just
Where is it?
5.3, the bottom of 18 to 61, the equation 61. I am, so a differential operator acting on this function, you can pull it out.
60, 61.
Yeah, bottom of 18, low 5.3.
I'm getting there.
What?
Oh yes, this is Nathan's.
You said that this was a cool thing, right?
Oh no, the cool thing is section 5.3.
I'm sitting here.
This is an amusing thing. I wouldn't classify it in the world of cool.
Sorry, Nathan.
Oh, don't worry. The cool thing in section 5.3 is Nathan's, as he called it originally, the stupid solution. It's far from stupid.
Theorem 5.3?
No, section 5.3. So it's called solution by extension. Let me show you how it works.
Okay. Let me see.
Here, I'll just show you how it works. And then I'll justify it for you next time we meet. There's actually a fair amount leading up to the results here, but at the end of the day, it's something you can teach engineers. So you want to solve, something like y prime prime plus 9y equals to 0, right? Okay.
Mm-hmm.
So you say, all right, characteristic equation, k squared plus 9 equal to 0.
Mm-hmm.
Great.
I want to get an imaginary 3 out of it.
Then I take e to the kx,
Okay.
and I look at what that is. That's 1 plus kx plus 1/2 k squared x squared. Right?
Mm-hmm.
But you're right. This says k squared is equal to -9.
Yeah, 3i.
We can think of k as being 3i, right? So really, this is essentially like e to the 3ix. I mean, that's how it kind of behaves, right?
Mm-hmm.
But I don't want to write that because I'm not saying it's I, but it does follow that pattern. So it's completely unsurprising that I write this is the cosine of 3x plus k times the sine of 3x, yeah?
Mm-hmm.
And instead of x, let me use t here. Question. What's the solution to this differential equation? Oh, that's right. Yeah.
Yeah, C1 cosine beta t plus C2 sine beta t.
Yeah. Great. Solve. Y prime prime equal to 0. So I'm looking at k squared equal to 0 this time. I do e to the kt. 1 plus kt. Stops there. That tells me that y is equal to c1 plus c2t. Because those are the functions that appear in the exponential. Those are the special functions. 1 and t are the special functions of the characteristic algebra. Cosine 3t, sine 3t are the special functions of the characteristic algebra. This one. So, great. K squared minus 2k plus 1, also known as k minus 1 squared, equal to 0.
I mean, yeah, it's like
Still,
C1.
I look at e to the kt.
You get 1 plus KT.
I gotta be a little bit sneaky here. If you could do that, it would lead to much suffering. So what I'll do instead is this is k minus 1 plus 1.
Okay.
Which is e to the t to the k minus 1 t.
Wait, that's the...
Right?
Mm-hmm.
So this tells me e to the t times 1 and t e to the t. Well, excuse me, I'll write this one more step here. This is e to the t minus t e to the t plus k times t e to the t. Alright? So in this case, y is equal to c1 times e to the t minus t to the t plus c2 t to the t is the way I would do it. Just on the basis of like the method. Of course, you identify that like we've just subtracted a copy of this over here.
Yeah.
So you can get rid of this and just have e to the t plus t e to the t, which of course you can recognize is what you should have here because you have a repeated root of 1.
Yeah.
Multiplication by t. Multiplication by t is derived from the extension algebra technique. Sine and cosine as solutions are derived from the extension algebra technique. We have one other case for a second order problem. Distinct roots.
Yeah.
How's that go?
C1.
Let's try one. Y prime prime. Let's say minus 3y prime plus 2y equal to 0.
Yeah. It's like R1. It's like C1 E R1, right? Plus
Yeah. What case?
C2 E R2.
Oh right. I'm sticking with my K notation, but yes, I agree with you. So that's a kind of funny.
Yeah, that's what plus 2 minus 1. Or
Yeah, we could factor it, but I don't know if that would be
no, it's minus 1 minus 2.
minus 1 minus 2. I mean, yeah. I mean that might be. I could maybe play games with that. I don't know. So here it is, e to the kt, right? And so the thing is, k squared equals to. Oh! I know what I have to do. I'm fast. I'm going barreling down a road to nowhere. The way to do this, it's always completing the square. So we have k minus 3 over 2 squared equals to 1/4. Okay, so e to the kt, e to the k minus 3 halves plus 3 halves t, e to the 3 halves t, right? And then we have e to the k minus 3 halves t, which let's see here, how's it go?
the same?
Well, I had a minus here, got a plus here.
Well, I'm talking about.
I I can start writing it out. I mean, this is 1.
Yeah, plus k minus 3 over 2t.
Yeah. Right, so what's that, how's that work out? This is a quarter, right?
Mm-hmm.
So, but I really should think of this as 1/2 squared. It's more productive. See, because then this becomes 1/2 squared, which becomes t over 2 squared. And then the fourth, and then you get 1 over 4 factorial, t over 4, t over 2 rather, to the 4th power. And then the odd terms, you get 1k minus 3/2 left over, but you got yourself a t plus 1 over 3 factorial, t over 2 rather, t over 2 cubed. And so what I'm really saying is e to the 3t, this is a cosh of t over 2, plus k minus 3/2 sinh t over 2.
That's not a. Well, yes. I mean, that doesn't.
So now, so our solution is like y is equal to like c1 e 3t cosh t over 2.
Mm-hmm.
You know, minus 3/2 sinh t over 2, right?
Mm-hmm.
That's from this one and this one. And then plus like c2. Oh, I'm bad. Okay, yeah, that's the real component. And then the other k component would be e to the 3t sinh t over 2, right?
Yes.
Now, and it wasn't 3t, it was 3/2. I somehow lost my half here. See that? Right?
Yeah.
So what is e to the 3t over 2 times cosh t over 2 anyway? It's 1/2. 3/2 plus 1/2 is 4/2.
Yeah.
That's e to the 2t. 3/2 minus 1/2 is 2/2.
Minus 2t. Oh.
No, it's plus 3 minus 1, so
Oh,
2,
yeah.
2,
Yeah.
it's 1.
1.
So, see, the e to the t, e to the 3t cosh t, and e to the 3t over 2t sinh t, they either give you 1/2 e to the 2t plus e to the t, or 1/2 e to the 2t minus e to the t.
Mm-hmm.
These are just linear combinations of the usual, you know, this is the, you know, the usual solution by your course, right?
Mm-hmm.
No, I mean, obviously that is like faster, right? No doubt out. It is somewhat ironical, to quote Dr. Wayne, where I used to work. One of my colleagues used to say ironical, to keep me dry. But actually he would say, it's very ironical. But anyway, So it is somewhat funny that like the simplest case of differential equations, it just makes the algebra for this method kind of be messier.
Mm-hmm.
But I would like you to see that I've solved all different kinds of the second order problem using the same calculational technique, which is simply recognize the characteristic algebra for the problem
Yeah.
and write down the exponential for the characteristic algebra. Recognize then that the component functions to the exponential are the solutions to the differential equation. This technique still works when the differential equation is over an algebra, not over the reals.
Wait, what?
Right. Wait, what indeed? So, here, let's look. Jay-Z's been in the news, right?
Yes.
That was the news. How about W prime prime plus JW equal to 0.
Same thing.
So we do like k squared plus j equal to 0.
Mm-hmm. Minus j.
Yeah. K squared is minus j. I avoid square roots. Bad news. But anyway, the point is e to the kz here, where z is the algebra variable,
Mm-hmm.
is since k squared is minus j, we can write this. This is, I guess I could write it. I write this elegantly.
We're the same way. I would say 1 plus 1/2 or 1 plus k kzt or no kz plus 1/4.
Yeah, I mean I've got the sum, let's say n 0 to infinity of like kz to the 2n.
Mm-hmm.
We have the even terms, and I'll use m as in mommy. The odd terms, right? I mean, these are the two kinds of things in this series
Yeah.
for the exponential.
Then you get your sinh.
Yeah, let's see here. So k to the 2n is what? It's minus j to the n, right? And so like this is minus j to the n, then z to the 2n over 2n factorial. And this one.
Mm-hmm.
But actually I'm not enjoying this calculation at the moment. I'm going to erase this and go a different way.
Yeah, but I thought we had a definition already.
What's that?
Like cosh x is equal to the sum of j equal to 0 to infinity of 1 over
Yeah.
2j factorial.
Oh yes. I mean, it is of course true that you could write this as like cosh of kz plus sinh of kz. That's really what I had just written with power series notation.
Mm-hmm.
Cosh is the evens, sinh is the odds. That's true. But let's see here. So this is really 1 plus kz, 1/2 kz squared, right?
Yeah, or that's
This
j
is-
minus j.
Yeah, kz plus 1 over 3 factorial, right? Kz cubed, higher order things. I just wanted to do that much to get the pattern rather than like burdening myself with the full series. So what happens? K squared was minus j, right? So this is really 1 minus j over 2 z squared, and plus kz, which is what it is, and then plus 1/6. Well, really, there's a k here I can keep, but the k squared becomes minus j, right? Z cubed. So getting to the point, there's a real component and there's a k component. I shouldn't say there's a real component. There is a hyperbolic component. The hyperbolic component here is 1 minus j over 2 z squared. I think that's it. These two got k's, right? Plus stuff. And then plus k times z. Now you're saying like this is just a sinh or a cos or something. I think you might well be right, but it's not quite that because it's like that j. It's messing with us. Z 1 over 3 factorial jz cubed. So that it's kind of sort of like a cos and sinh, but it's not quite that because it's got the j and but not the j, and it's flippity floppy back and forth having no j or having a j, and but nevertheless, this right here you could call W1. This right here you could call W2, and I'm pretty sure the solution has the form C1W1 plus C2W2.
Take your word.
Yeah, I have not proved that yet. And, I mean, we could try it out, right?
Yeah.
To try it out, let's see here. We should take W1 prime prime, what's that?
W1 prime prime?
We differentiate this twice with respect to z, we get
Like 2 over.
yeah, minus j over 2 times 2 times 1, right? I mean, like, you differentiate twice, the z squared differentiates down to 2, you got minus j, right?
Yeah.
And so we're like, it's W1 plus stuff, right?
Yeah.
But up to the order that I have listed here, W1 prime prime plus j W1, what do we got? You got yourself minus j plus j times, what's W1? W1 was 1 minus j over 2 z squared, right? Stuff.
Yep.
So you can see what's happening. To first order, we've got 0 plus stuff.
Yes.
So like to the calc, I mean, yeah, it's going to work. And likewise here, like when you differentiate this twice, there's going to be like this interplay between j times the function, and it's going to pick up like a minus that's going to cancel like this term and that term. We're going to cancel and put them up into here. But you need the j to balance that j. It can't just be cosh and sinh. It's got to be like this kind of, it's kind of coshy, it's kind of cinchy, but it's not a cinch. It's not a cosh, it's something else. But it works. Nathan's stupid solution works. Now this was not, this may be a little bit past his, but there's a couple different, I mean, so the funny thing is, in differential equations, the idea that you can solve the differential equation when it has complex roots by like what's called the complexification technique. It feels like an outlier in differential equations because everything else you do by other methods, so just use exponentials or whatever. And yet that complex case requires us, at least from one perspective, complexification. What we ultimately learned though is that complexification is the general technique.
Over algebra.
Because that's how we can solve anything by